Okay, so now I want to come on to the different parts of the network and what sensors we use to detect PD. Okay, so like I mentioned earlier, the PD sensors that are used across the industry. So what you'll find is that other PD manufacturers will use the same type of sensors. And although, of course, I would claim that these sensors are the best sensors manufactured in the world, and of course I would be correct in that assumption, fundamentally everybody uses the same type of sensors, and it's not necessarily so much the sensor, although the design and the characteristics are very important. It's not so much the sensor, but it's more important is what you do with the data output. So HFCTs are relatively simple electrical devices, but it's what you do processing that data output which really makes the difference. And so that's applicable to all of our sensors. HFCTs, TEVs, ultrasonic sensors, in and themselves, they're very simple devices. The concepts are very simple. The sensor design is important but not critical, and what is critical really is what you're doing with the process, how you're processing the data afterwards. So for underground cables, we use a HFCT, high frequency current transformer, and that HFCT, they come in different shapes and sizes depending on where they're going to be applied, and we can apply the HFCT to cable earth sheath. We also apply the HFCT around the core of the cable, and I'll explain why next. So in this example, I've put the HFCT on the earth sheath here, but you could also install the HFCT around the core of a cable there. But importantly, the HFCT needs to be installed on one or the other. It cannot be installed in a place where you're capturing both. The reason is, when a PD occurs on an underground cable, what you'll find is the PD will be induced on the core and also on the earth. So you get equal and opposite signals being induced on both parts of the system, if you like. So what it means is if we put a sensor here, for example, we would be surrounding the earth and the core and we won't detect any signal. That's not incorrect, actually I should say here we wouldn't detect any signal. So if we install a HFCT on a core, it needs to be a core without the earth, and if we install a HFCT on the earth, it needs to be the earth without the core of the cable. So we need to find a point in the network where we separate the two. So on medium voltage networks like this one here, medium voltage networks tend to be HFCTs are installed in the cable termination. They're installed back in the substation, and quite often they're installed on the earth sheath, particularly for spot testing, because the earthing tends to be more accessible. So that's where HFCTs tend to be installed. You can install them on the core, and in fact on the core you would get a more accurate signal. You'll be able to detect PD a little bit lower if you install it on the core. However, that's not always possible depending on the makeup. A shutdown is required for that installation, so it tends to be on the core when it comes to permanent installation or when it comes to a permanent solution, whereas installing for a temporary application tends to more be focused on the earth sheath as well. Okay, so if we zoom in now to this this area of the cable, let's have a look what happens. So again, this is most likely to be in a cable joint, but for simplification, I've took the sort of ideal solution. We've got a single core cable, high voltage cable, and the earth shield around the outside. Now, when a PD occurs, when one of these very small PDs occur during the rising edge of the power cycle, what happens is PD is then induced on the inside of the earth sheath, and also an equal and opposite signal on the outside of the core. So what that means is those two signals, because from the PD source it's emanated away, it's then been induced onto the inside of the earth, the outside of the core. Those two signals are equal and opposite. So if you put a sensor around the cable, you won't detect anything. So that's why we can apply HFCTs around a cable, because we've got those equal and opposite signals inside. Those signals are traveling along the surface. They are trapped inside. They're high frequency signals. They're trapped inside the cable because the cable acts as a Faraday cage, so the signal cannot escape. But what happens is they will, from the PD source, they will travel away from the PD source along the core and along the earth. Now again, I must emphasize these are, with all PD signals, these are high frequency signals, so it's not high current, it's not a load traveling along the cable, it's a high frequency, very fast moving signal. So this high frequency signal is traveling along the inside of the cable, and it'll travel. So if my animation works this time, it will travel, there we go, it will travel along the inside of the cable earth in our example, come out at the switchgear and through the HFCT. Now, detecting PD on the earth sheath, the earth must be isolated from the switchgear. If the earth is not isolated from the switchgear, the PD signal will enter the switchgear and be lost. So it's important for the earth to be isolated from the switchgear. Now, when it comes to the lower end of the medium voltage, maybe 11 kV, 10 kV, whatever the standard is in your country, sometimes this may not be the case. Either an installation engineer has made a mistake, or it's not a standard policy to isolate the earth from the switchgear. When we get to the higher voltages, when we get to the HV level and the EHV level, when we're in the hundreds of kVs, obviously the earth is definitely isolated from the switchgear. But in the lower voltage levels, this may not always be the case, and it's always worth checking that situation out before looking to apply this type of technology. If they are directly connected, if the earth is directly connected, what it means is that the HFCT must be installed on the core of the cable. Normally that also means that it must be installed inside the termination. So again, the only place where you can separate the two sometimes is on the core of the cable. Case by case, we look at that with customers, and always happy to help and consult if anybody is in doubt. Now, just a note on EHV. So on extra high voltage circuits, what tends to happen is along the circuit themselves, there is link boxes, there is cross-bonded joint locations. And so what it means is we also have extra opportunities to install HFCT sensors. On top of that, EHV cables tend to be very long. There's quite a long distance, and so what it means is it's quite useful to install at different points, because the typical range of a HFCT is about 4 or 5 kilometers. And so on an EHV circuit that is maybe 15 or 20 kilometers, it's quite nice to be able to install HFCTs along the cable length. Equally, installing sensors along a cable means you get that increased sensitivity. As you would imagine, the smaller PDs are detected more easily, so it is better in EHV applications to install sensors along the actual circuit itself. And the nice thing with EHV, of course, is the earth is separated from the core at these points along the installation. Just another note is they're not necessarily the nicest environments. However, although they're not the nicest environments, we do have solutions for monitoring in these environments. So we can monitor with IP-rated enclosures, we can use fiber optic for communication, and we can install underground. Okay, so looking at on the switchgear side, then medium voltage switchgear, what we tend to use is CCTEV sensors, as we call them, capacitively coupled sensors. Essentially, they're also more commonly known as just TEV sensors. Many of you will be familiar with TEV devices. Handheld TEV devices have been used in the industry for many, many years. And in fact, many companies, that is their only familiarity with, many engineers, that's their only familiarity with handheld, with PD test equipment, if you like. So PD test equipment, the TV sensors are often built inside, so like this one here. So the head of the sensor is a TEV sensor, but also you can get them in external individual sensor types, which is what we use on our permanent monitoring systems. The sensors themselves are relatively simple. They're a capacitor. So one side of the capacitor is the sensor and the other side is the switchgear. And so if you get these high frequency signals occurring across the surface of the switchgear, these capacitive, these CCTEV sensors will be able to detect this signal. So what happens is very similar to cable PD actually, just in a different enclosure, a different environment. When PD occurs in a high voltage component, the signal will dissipate from the source, and it will be induced on the inside of the panels within the switchgear. So on the inside of different panels, and then it'll travel away from the PD source. So again, just like cables, it's trapped inside, it's traveling along the surface, and what happens is it comes out through the gaps in the panels. So where two panels are attached together, it travels out through the gaps and along the outer surface of the equipment. So it travels along the outer surface of the equipment, and then it travels across the surface of the TEV sensor, be that either built into, like I said, built into an instrument or physically attached. And then that signal is induced on the sensor. So what it looks like with my, if I just flip through. So what it looks like, a PD will occur in any component of the switchgear, remember, anywhere where the installation may be, the insulation may be weak or damaged, will occur, and then travel along the surface of the equipment, out through the gaps, and out across the front surface of the sensor. The PD travels in all directions away from the PD source, and actually on TEV, the TEV signal, so the cable, like I said, it travels about 4 or 5 kilometers. The TEV signal is a much higher frequency signal because we're a bit closer to the PD. So the TEV signal will typically travel about 4 or 5 meters, after which it will attenuate down to 0. So what it means is when you're detecting PD on switchgear, you're most likely to see it on many panels across the switchgear surface. So here's another one of my fantastic animations. So out from the gaps in the panel and being induced across the surface of the TEV. Out from the gap and induced across the surface of the TEV. Now, it must be noted that PD, again, will travel in all directions away. It'll travel across the surface, across many panels. And so just because you're detecting the PD on one single panel does not necessarily mean that's the source of the PD. And I'll comment a little bit later on how we would attempt to locate those things. The next one then is the ultrasonic sensor. Ultrasonic sensors are ultrasonic detection on switchgear is very simple. It's a 40 kilohertz microphone, one of the most simple sensors that you can create, that you can make. Also, the interpretation and the detection of the signal is also very simple. Quite often you use them built into the head of handheld instruments, put some headphones on and point at where there may be some surface tracking occurring. If surface tracking does occur, the sensor is very, very sensitive and will very easily pick up that signal. So we have sensors for permanent monitoring systems, and we also have sensors that we build into the head of devices, like in this next image. So built into the head of devices to pick up the PD. Now, modern switchgear tends to be more enclosed, so the locations that we can apply our technology, the locations where we can apply our ultrasonic sensors, can be more limited. However, where they can be applied, it's very, very sensitive. What we tend to do now with permanent installations is we'll install the sensors inside the cable termination. So it's quite common for us now to look to take a shutdown, to install the sensor very safely, run a connector outside so that in future you can use portable equipment to test or connect it to a permanent monitoring system as well. Here's another animation. Ultrasonic sensors are very directional, it must be noted. So they generally have a field of view of about 30 degrees. And so they're good for about 2 or 3 meters, and they're very directional. So the nice thing about ultrasonic is your location is conducted at the same time as your testing, if you like. So as you swing the device around, you're pinpointing the location as well. This picture on the left is actually quite a nice picture. It shows another type of partial discharge that can occur. This is not caused by, well, I suppose to a certain extent it is caused by weak insulation. But the main problem here is what's happened is the 3 phases are coming inside the termination. The insulation has been stripped back, but the insulation has been stripped back a little bit too early, if you like, and the phases are too close together. So what we've got here is these 2 phases with, this is where the insulation is ending. Some of the insulation is ending. So the very thin insulation here, and the phases are too close together. and so you get this discharge occurring between them. Now, of course, visually we can see this, but before it was visual, the ultrasonic sensor would be able to pick it up. Okay, the final sensor type I want to talk about then is UHF sensors, ultra high frequency sensors. So the application of UHF tends to focus on EHV GIS, and so the problem there is GIS is completely sealed, and so the only signals that escape from GIS are very high frequency, so ultra high frequency, and so naturally we use ultra high frequency sensors to detect the PD inside the GIS. What we use is if I go to the next one, so our sensors are, I mean, typically they're 500 meg up to 1.5 gigahertz, but they could be even more. Actually, IPEX sensors are about 300 meg up to about 2 gigahertz, and we install them on the barriers. So where the two components or two compartments of the GIS, where they meet, there'll be a barrier in between, and we install the UHF sensor there. That's where we're going to see this ultra high frequency signal, which is going to escape from within the GIS. Quite often, I mean, there's lots of different barriers around the equipment, so quite often we install them where the customers have the main concern. So sometimes the main concern is in the CT or the VT or the circuit breaker. Depends on the switchgear, depends on the history of failures of that type of switchgear. Quite often it's also on the cable termination. Cable terminations are naturally a weak point in any equipment. So I think this picture here is a cable termination, so installed on the barrier of a cable termination there. Thank you very much for your time. Hope you learned something, and watch out for new information that we'll be sending through. Thank you.